the real integral is in the form this uh, on the real axis. It's integral infinity to infinity, some function of real number dx, and then integrate along the real axis or along when x is minus infinity infinity. Okay, so obviously that you learn calculus, you know that this infinite limit just means it's taking in the sense limiting case. Whatever you use the fundamental theorem of calculus, you evaluate or whatever you have in that limit of minus infinity to infinity. Okay. So that was assuming well understood, but the first thing, of course, you try to see the integral is well defined or not, and that require f to be bounded somehow bounded at infinity. If it's not bounded, obviously integrated to infinity, then you will have trouble. So usually the bounded condition will require that fx as large x will decrease to zero, and not just decrease to zero, but it's decreased fast enough, and usually faster than 1 over x. It will decrease to zero less than slower than 1 over x, then you'll get into trouble because dx over x will give you a log. Right? If it, but if it's dx over x 1 plus a little positive number, then you still get 1 over that positive number. 1 over x over give you 1 plus will give you 1 over x over, actually I should multiply by minus over, right? Minus over. Okay. But indefinite integrals, something like that, right? So you has to have a 1 here in order to get to here. Alpha is positive. Then evaluate at the large x to give you 0. If it is if alpha if integram degree less than 1 over x, meaning alpha is negative, then this becomes in the numerator. Then the positive limit will give it the divergent result. So the integral will not be well defined. So usually the integram for well behaved integral supposedly for large x is increase at least 1, decrease to 0 at least 1 over x. Okay, and so that just from the integral, you know that it must satisfy something like that. And for using the complex method, the same thing happened. So for this method, at least you require that that the limit of basically we'll transform that and evaluate that as a complex variable. So this becomes integrate along the z-axis. So you require that limit of c goes to infinity, or magnitude of c goes to infinity, and c equals to 0. So we require that. But this method doesn't have to be uniform here, and usually when it happens, part of it, then the other part will also satisfy. But you can actually limit it to just half of the plane. That would be fine, because the way to do it is you extend it to the complex plane, this Z plane, and then the integral is integrated along the real axis. So that's the original path, so minus infinity to infinity. So in order to use the residue theorem, you want to form a closed loop, and one way to do it is just connect this minus infinity and infinity by a big circle. So you can either go positive and form a loop like that, right? And say this is your original I on the real axis, and there will be a large infinity, I infinity along this circle. And the way to argue is that if this condition is satisfied, then the path integral along the big circle will be 0. There will be no contribution from that, but you still get the whole loop. You form the whole loop, but with the other part is 0. Then the solution obviously is just summing over the residue on the upper plane and then multiply by 2 pi I. That would be your the answer for the integral, right? So sometimes you use it this way, close it on the upper plane, but sometimes maybe one way is more convenient than the other. You may close it to the lower plane, and then the loop will be the same loop and the same argument that this is I, maybe what define another name minus infinity loop. And if this condition satisfied on this path, then you can argue that this integral along here is 0, and then you get the sum over the residue here. But when you close the lower semicircle, then you need to be a little careful about the direction of your integral, because now this is in the clockwise direction, so it's not the same sense of direction as the residue theorem. So for here, for the upper plane, close in the upper plane, so I will be just 2 pi I and move the residue on the upper plane. If you close it below, then I will be minus 2 pi I. Look at the clockwise direction, minus 2 pi I, sum over residue on for the poles on the lower plane. Okay, just the sign you need to be able to whether you close it upper or lower. Is that okay? So that's the four. And I mean the justification of this one should be straightforward, because I mean the textbook has some argument if you want, but a quick argument says this magnitude, which is the integral of that, so you can say that the integral, if consider this I infinity, the magnitude of that is going over this C infinity, and F dc, right? So this magnitude will be less than the integrated over the argument of the function dc. Okay, and dc over here. So that's some theorem you need to cite to satisfy this inequality, to justify this inequality. But we just assume that it's you know that. I mean, you can just hand waving understanding this is after you do the integration, take the magnitude. So the integration supposedly you have positive and negative and complex, and there's cancellation within it. Then should be less than you take the magnitude of the integral first and take the integral later. Okay, so that's the basic idea of these inequalities right there. And now this DC is along the big circle, so this assume it be R theta. So DC, let's see, on this is R E phi theta. So DC is R I E I theta. And supposedly you can actually we should put all this inside here, but that these are just argument of unity, or I theta is argument of unity. You put it inside here, and that would be by this argument, this is all, it's just the magnitude of z, and f is just here, so that's tends to 0. Right, and this integration is just the range of the angle, which is just for here just pi, so that's go to 0. That's L goes to infinity. 0, not infinity. Okay, so this justification is quite straightforward, but we just need to remember this condition. So the f has to be at least goes to 0 faster than 1 over z in order for this method to work, which is to say again the same as whether f exists when the argument is large. Okay, now let's see. Let's do an example, and let's see how many examples here. But this is one, so 11.8.3, which is very straightforward. Example 8.3 I is over 1 plus x squared, and the limit is 0 to infinity. Okay, and first you noted that it's not minus infinity to infinity, and but we can change this integral to this form by looking at the integral is an even function. You have x squared here, so you can say that this integral is the same as the integrating from minus infinity to 0, because it's change x to minus x is the same, right? So you can say that is this one type of integrating minus infinity to infinity. So is that okay? The first step. Now this condition obviously is satisfied because at large x is decreased as 1 over x squared. It's faster than 1 over x. Then you can figure out the pole. With the same view. Now you extend it to complex plane. Just change x to c, and the factorization is trivial. Right? This is 1 over 1 plus c squared becomes c minus I times c plus 1. So there are two poles. Yes, erase that. Well, it doesn't have to. It's just one is I. Right? There are two poles, and both are simple poles. And you need only one of them. You can either close up or close down. But this case doesn't matter. It should be the same. If you close it above, then this is you know 2.5, and the residue is multiply c minus I, cancel with that, and take the limit c goes to I. So 1 over 2I. Okay. And this is I can cancel. Okay, and finally, of course, you check that it's real, because the original integral is real. So After all that, you will get a complex number. Then you need to do it again. Yes. And this should be the answer in the way. All right. And for this simple case, you can do it using some elementary methods. You probably learned that in calculus also. Some substitute, either sine, cosine, or tangent, or something like that. All right. So